Let's look at this interesting question. So we've got two blocks sitting side by side on a table. Block A has a mass of 1.5 kilograms and block B has a mass of 3.4 kilograms. These blocks are being squeezed together by two applied forces. Block A has a 4 Newton force pushing on it, while block B has a 2.2 Newton force pushing on it. And our eventual goal here is to determine the acceleration of the blocks. Now what I didn't mention here, which I really should have typed out, is that we're going to assume that this is on some sort of frictionless surface. We're not worried about friction yet. Either that or the friction is going to be negligible, meaning it's so small compared to the other forces we can ignore it. Okay, so before drawing here, draw a free body diagram for each block separately, let me actually take a moment here and just sketch out what's going on with the problem in itself and see if we can make any predictions. So we've got two blocks going on. One block has more mass than the other. I'll just kind of draw them as different sizes to represent that visibly. They may not be different sizes, but regardless. Sorry, I'm having trouble here. Alright, so we've got, again, my pen is in the process of breaking. Alright, call that block A. We'll call this block B, sitting next to each other. Let me actually make this a little thinner. Alright, we're told that there's some sort of force, F1, pushing on block A that has a strength of 4 newtons. We're told that there's a different force pushing on block B, we'll call that F2, that has a magnitude of 2.2 newtons. So looking at this, kind of a prediction we can make, well, first, both these blocks, they're forced to be moving together, right? They're touching each other. We've got these forces acting on them, so when they're moving together, not only are they going to have the same velocity, but they're also going to have the same acceleration. So acceleration will be the same for both. And another thing we can predict is looking here, we got 4 newtons and 2.2 newtons. The 4 newtons is going to kind of win out, so we expect that our acceleration is going to be rightward. Alright, so those are our predictions. Let's see if our problem, if we get that. So let's draw a free body diagram for each block separately. So let's start with block A. So for block A, alright, we draw a dot to represent the object. Let's see, the block is sitting on a table, so one thing we always draw is the force due to gravity. So that's going to be acting straight down. Alright. Alright, and then we also have a normal force straight up. Alright, so force of gravity, normal force, those are going, I drew them the same magnitude because our blocks are accelerating horizontally only, not vertically at all. So vertically my forces has to cancel out. Now horizontally, we do have acceleration occurring. Just kind of sketching out forces. Well, we've got for sure a pushing force, which I referred to as F1 before, so I'll continue to do so. Alright, so that's some rightward force of F1. Now the other, we do have one more force going on. Right? We have the block is touching another block. So we have the force of block B acting on block A. Right, and that's pushing to the left on this object, right? Because it's pushing back on block A. So I'll call that the force, we'll call that AB. Alright. And that's all the forces going on for our block. Now let's look at block B. So I use a dot to represent the object. Alright, we also again have a gravitational force and a normal force. Again, these are going to be equal and opposite. I'm going to draw my gravitational force, though, larger because it has a larger mass and therefore has a larger weight. Alright, now let's worry about our horizontal forces. So we have the force 2 acting on it, the 2.2 Newton force, as well as the force of block A acting on block B, because they're in contact. So here, well, we can draw the reaction pair force for the contact force. Now, something I should be careful about, though it really doesn't look like I am being that careful about it, is that these forces, these arrows, are equal in length and opposite in direction. So let me actually make this vector a little longer to better represent that. So those are equal in magnitude, opposite in direction. So then now I'm going to sketch out the pushing force that we have acting on block B, which is acting to the left. And since I know that these two objects have the same acceleration, and like we predicted, acceleration is rightward, I'm going to draw this a little shorter. And that is force 2. Alright, so here we have a free body diagram. Now if we didn't go through the step of predicting what the direction of the acceleration is, that's okay. It doesn't really matter the relative sizes of these too much, at least for the time being, of the different vectors I mean. But it's going to, I just decided to do that because it'd be a little bit more useful. Alright, part B. Use Newton's second law to set up an equation for each free body diagram. Alright, so Newton's second law says net force is equal to mass times acceleration. So then, doing that, since our eventual goal here is to solve for acceleration, it's not going to be useful to set up applying Newton's second law for the vertical direction for both these blocks, since it just all that's going to tell us is that the gravitational force is equal to the normal force. We'll do that if we have to, but spoilers, we won't. So here we have the sum of the forces. So again, the Greek letter sigma representing sum of the forces in the x direction for object A is equal to mass times acceleration. Now carefully, we have to say this is the mass of block A times acceleration. So I'm using a subscript there of A to represent that. Now I didn't set up a coordinate system. Let's do that. I implicitly applied a coordinate system here. We'll call, okay, taking a step back here. The problem solving strategy, I always recommend calling the direction of acceleration positive. That's going to make it, when we have more complicated problems, make it easier to solve, because we're going to have to worry about negative signs less. So we're going to call rightward our positive x direction. So here then, any rightward forces will be positive, and any leftward forces will be negative. So this means we, looking at our free body diagram, have a positive F1 and a negative contact force between the two. And secondly, we can sum our forces horizontally on block B. That's net force. That's equal to mass times acceleration. Again, we have to be specific as to which mass we're talking about. And that times acceleration. Looking at a free body diagram, now we have a positive contact force and a negative force 2. Now something I'll explicitly mention, maybe I should have called my free body diagram for block A, this F with the subscript of BA, since that's the force of block B acting on block A. But I kind of jumped the gun here and said, well, I know that these are equal magnitude opposite in direction, so I'm just going to call them force FAB, because I know they have the same magnitude. Alright, so let's solve this system of equations to find the acceleration of the block. Alright, so system of equations, right? So we have two equations here. So why is it important that we're dealing with two equations? So let's look at how many unknowns we have, right? So in our problem, let me scroll back up. Oops, that is not how I scroll. There we go. In our prompt, we're told the mass of block A, told the mass of block B. Right? We're told F1, and we're told F2. So those are our known quantities. So looking at our equations here, the system we're solving is this, where we know everything except for two quantities. We don't know acceleration, and we don't know this contact force. So because of that, then we have two equations, two unknowns we can solve this system. Just be careful. Sometimes you might have too many unknowns and you can't solve a system of equations. So something to be wary of. So solving this system, all right, I'm going to just rewrite it just because that helps me. So we have the mass of block A times the acceleration is equal to F1 minus FAB. And the other equation is the mass of block B times acceleration is FAB minus the second force. So what I'll do here is I'll take this second equation. Our end goal, like we said in the problem, is to solve for acceleration. So we have to take one of these two equations, rearrange for the unknown we don't care about, which is FAB, and use that and substitute it into the other one. So looking at this, I think it's going to be quicker math to rearrange this second equation. All I need to do is add F2 to both sides. We find that FAB is equal to mass of block B times acceleration plus force 2. So now we have an expression for this contact force. We can plug it into our first equation. So we've got the mass of block A times acceleration is F1 minus this whole expression. Mass of block B times acceleration plus force 2. So since we're trying to solve for acceleration, I have two terms here with acceleration. So we need to isolate them, or combine them into one term. So I'm going to first distribute my negative sign. I'm going to do that in this step just to save a little space. Alright, so then all I'm going to do now is add my mass of block 2 times acceleration to the other side. So we have the mass of block A times acceleration plus the mass of block B times acceleration is equal to F1 minus F2. So then we have, we have to isolate this. So we pull out acceleration from each term. So basically we have acceleration times the combined mass is equal to F1 minus F2. And what's nice now, a couple seconds left, all right, is that we can plug in the numbers, once we write our acceleration expression. And all I did here was just divide by the total mass to isolate acceleration. And now I'll plug in the numbers. Alright, so plugging in the givens from our problem, we end up with an answer of positive 0.37 meters per second squared. And we got a positive value, which is rightward, which seems reasonable for our problem. Alright, we will continue talking about this problem in the next video.